Hello, everyone. This is our part five on climate change. So, first of all, in this lecture, we're gonna look at the anthropogenic carbon emission. What is the role of humans in climate change today? First of all, let's look at the graph. The graph below illustrates the changes in CO2 concentration over time. You can see, for example, here from 800,000 years all the way to today, you can see that the fluctuation in carbon dioxide in ppm. And here you can see this higher value. Like, for example, 2012, we have about 400 ppm. And in the lower emission model in 2100, the scientists predicted this amount of CO2, which is about 700, not 700, probably 550 ppm. But the higher emission model goes up to 900 ppm. So also here we have CO2 concentration from 1750 all the way to today. You can see again the rise in the carbon dioxide, and this CO2 here is measured from the ice cores, from the bubbles, remember? And from here, from 19, anyway, right here, before 2000, we have direct measurement. So around which year did the CO2 levels begin to rise sharply? What do you think caused this significant increase? So here we can see that along this 800,000 years, the values of CO2 did not really go higher than 300. But right around here, it starts to go up sharply. And you can see it also here. What do you think caused such increase? In fact, it's the Industrial Revolution starting in 1800 that where this increase in CO2 sharply increase. So the CO2 concentration has steadily increased well above that level to over 400 ppm right here. More than 400 ppm, reaches around 413 ppm. But studies of the ice cores shows that the amount of CO2 go from 180 to 300 ppm over this 800,000 years. So only when you get to here, when Industrial Revolution started, we have this sharp increase. And again, the reason is around 1800, we discovered the oil, we discovered the coal, and we start to use extensively these resources that emit a loss of carbon dioxide in the air. We have also other things such as cement, because cement, when you use cement, you release carbon dioxide in them, and so on and so on. So the healing curve left shows the measured atmospheric CO2 from top Mauna Loa since 1955. You can see again that here we have an increase in CO2 with the fluctuation up and down caused by seasons. Now, because the photosynthesis changes along the year. In spring and summer, we have more photosynthetic mechanism, which cause the removal of CO2 a lot in the air, and that's what causes this drop in the concentration of CO2. But during winter time, we have an increase of CO2 because the tree did not remove the CO2 from the air. So this up and down here is what you see, guys, here, right here. Up, down, up, and so on and so on. This like cyclic pattern each year. And the whole thing here, you can see the trend that is going up. Same thing for the CH4. You can see an increase in the amount of CH4. You can go back 1,000 years. You can see that the fluctuation is almost the same. But once you start 1800, when Industrial Revolution started, the CH4 started to increase sharply. So now, how do you know it's not a coincidence? It's caused by humans. So if you look at this diagram, you can see two graphs right here. The black one here shows you delta 13C right here. And the red one shows you the CO2 concentration. So describe the trend of CO2 and delta 13C. So you can see here clearly that the CO2 amount from 1000 all the way to 1800 is almost steady. And once after 1800, the CO2 amounts start to increase. And because this is because of the industrial revolution, because of loss of pollution. At the same time, delta 13C start to decrease sharply right on 1800. It decreased sharp. Why is that? Remember, delta 13C is proportional to C13 of C12. So why this drop right here? The delta C drop, if this drop means what? Means you have a loss of C12. Let's put it down here. Let's write this down, this information here. So if you go back here, if you look at the drop here, this C12 is dropping sharply. So delta 13C decreases. Now remember, delta 13C is proportional to 13C over 12C. This means this also drops. And what makes this ratio to drop is because this C12 here increase. Remember, when the ratio decreases, this means the bottom one here increases. This is 12 right here, C12. So why C12 decrease? Which one has a loss of C12? Remember when I said that the plants, they prefer C12 CO2. The plants take this, or let's say those planktons in the sea, they prefer C12. When they take C12, they get buried and form what we call black shell or coal. So now, when this black shell is discovered, we take the oil from them and also the coal from them, and this biomass is, remember, rich in C12. So when you burn those fossil fuels, you release this C12 right here. Because remember, those black shale and coal, they have a loss of C12 because again, the plants, they remove C12 easily. Or the phytoplanktons in the sea, again, if you talk about the land, they have trees, plants. If you talk about the ocean, we have planktons. In both cases, the trees, they remove C12 easily. And the planktons right here, they remove also C12 also easily. So when they get buried, we have black shale here, and when this get buried, we have coal. So black shale and coal, they have a loss of C12. So once you discover this black shale, and we use those coal and fossil fuel trapped in those black shale, when you burn them, you release C12 in the air. This means in the air, we have a higher C12. A higher C12 means a lower delta C13. And that's what you see this drop right here. So CO2 increase right here, and that CO2 that is increasing is actually C12O2 because the fossil fuels have a loss of C12. So this CO2 that is released here has a loss of C12, which means that because you have loss of C12, means that delta 13C is lower. Okay? So the biomass, which is hydrocarbon in black shale and coal from buried plants, they have higher C12, which means lower delta 13C. And that's why they start to get lower because you're releasing C12 in the air, causing the air to become rich in C12 and causing delta 13C to drop. And that's a clear evidence that the responsible for this CO2 release in the air is us. There's no question about it because we can see it from this delta 13C. More C12 from the biomass, lower delta 13C. And again, it's explained right here, fossil fuel, ancient organic carbon, they have very low delta 13 because again, remember, lower value of this means simply a loss of C12. This burn, when you burn those fossil that have a loss of C12, you add light carbon into the air, which is C12. This causes delta 13C to drop. And this matched exactly the observed trend after 1800. We have more CO2 and delta 13 drop right here. Increase of CO2, decrease of delta 13C. So this is a clear signature that organic carbon that we have in the air comes from fossil fuels, not from volcanoes or oceanic sources, simply because volcanoes and ocean sources, like, for example, emission along a divergent boundary, like mid-oceanic ridge, for example, they emit carbon that is rather heavier. That's why delta 13C for volcanoes is heavier. So it's not coming from volcanoes. It's coming from us. Again, here we have another, um, the greenhouse gas, because you have emission of CO2, like burn of fossil fuel, cement production, release of CO2 when limestone is heated up. This CO2 here is released in the air. Fossil fuel release when coal is burned or oil from black shale is burned, they release also C12. Amina CO2, the release of CO2 will cause definitely higher temperature because CO2 is a greenhouse gas. Deforestation also, when you remove the trees, we end up having less trees. And if you have less trees, we have less trees that will be absorbing uh, CO2. So when you have less trees, we have less CO2 uh, taken away from the atmosphere. Methane, same thing, is a stronger but short-lived greenhouse gas, but it's very, very, very strong greenhouse. It traps the heat a lot. It comes from livestock digestion, rice, paddies, and landfills. We have also this nitrous oxide, which is also a greenhouse gas emitted by specifically by agricultural soils and fertilizers. So we are responsible for the global warming we have today. This carbon cycle, I'm not going to talk about this diagram. It's very complicated, but again, you can just look at it. It's basically it gives you an idea where this carbon is going to. It's like a water cycle: evaporation, condensation, precipitation, runoff, back to the water, and the cycle starts over again. Same thing for carbon here. We have here fossil fuel reservoir. It traps the carbon here. The um, there's an interaction between carbon in the air and carbon in the in the water, and so on and so on. Permafrost, of course, if you have here carbon, CH4 below the permafrost, it'll be preserved. But if this melt, if it thaws, basically CH4 is released. It's a lots of things going on here. We have also volcanoes, also they emit carbon, and so on and so on. Again, we have here the what do you call the sinks and source of carbon. The source of carbon include volcanoes, fossil fuels, decay of organic matter, and so on and so on. But the sink is the one that removes CO2 from the air. This solution of carbon in the ocean, weathering also remove carbon from the air. And that will be the end of part 5. Thank you.